started. And I wanted to point out one thing that I have changed on the syllabus. The Tuesday of Thanksgiving week. The university does not have classes, but I have decided to offer office hours. So during the time that I would normally be teaching 12:30 to through office hours 4:45, I'm just going to sit here with my Zoom room open, and if anybody wants to come by and talk to me, they can. And if you want to have Thanksgiving break instead, that is totally cool as well. I'm doing that because homework 5 is due after break. And so I wanted to give folks a chance to get some contact time. If you're not able to show up that day, I'm not going anywhere for Thanksgiving. I'm not doing anything. We're just going to sit here and live the dream and probably order Chinese food or something because I'm not a turkey person. But that means I will be available on email if you want to contact me that way with questions. Um, let's see. So homework questions. Let's go back to that. Any questions on homework 4 that you'd like to ask now?
Lisa,
Yeah.
I have a question. I'm a little confused about negative estimates. They are good or they are
Negative slopes. Is that what you
bad.
mean?
I saw estimates. I know.
Estimates.
Yeah, but I mean, let me see the homework, then I can tell you.
Okay. If you have an example question, I can pull that up and we can use that for reference.
Yes. When you work with the mini golfs in the different types of groups,
Hmm.
and then we have one question that um, the estimate is minus, in my case, is minus 10.4. They're comparing groups, and I'm not sure if it is good or
Okay.
bad.
So for the questions that are asking about group comparisons, so for instance, there's significantly higher, non-significantly higher, significantly lower, non-significantly lower, for instance. That's just literally which number is higher. So if there's a negative 10 difference, the group that is the alternative group is lower. So you can just take those at face value. The tricky part is what a lower score represents. For this type of outcome, which is your golf score, lower is better. So if you are in a group that has a 10-point lower score on average, then you have gotten a benefit of training because training has lowered your golf score. So there's a lot of instances in sports in which lower is better, right? How quickly can you run the marathon? How many strokes does it take to get through all 18 holes? So this is a lower is better kind of thing. Does that help? Okay, great. 2 thumbs up. That must have really helped then. What else can I really help with? Nothing? Nothing right now, anyway?
I
That's
have a question, and I'm not sure if I'm going to ask it right or ask it in a way that makes sense. So, in terms of those piecewise pairs or the piecewise um, effect,
mm-hmm,
we've got two. Okay, so there are. We're doing that above the 1 to 4 and 4 to 7.
mm-hmm.
And so that, as I understand it, that would be 2 fixed slopes.
Correct.
Okay, that's what I wanted to run by you. I'm glad I was able to spit that out in a way that made sense. But
Hmm.
okay,
Yeah,
that's
in
great.
in these models, the solution for fixed effects, everything is either going to be an intercept or a slope. So there will be a line that says intercept in SAS. It will say constant in Stata. That's the intercept. That's the expected outcome when all your predictors are 0, and everything else is a slope. I'm using the word fixed, which is atypical in a course like this, but it's because if you stay on with me, you will learn about something called a random slope. And so I wanted to set the stage that this is only one kind of slope. More specifically, what fixed means in this context is that everybody shares the same number. So the slope that is estimated, like if your slope is 2, everybody uses that 2 as a multiplier for their variable the same way. So it's a constant value. A random slope actually varies across persons. So contrast. But that's not this class, that's the spring class, which, by the way, I know schedule of classes came out. I am going to send you all an email that I'm asking you to circulate if you have classmates or peers who are interested in taking this class, because this class is not going to be a thing anymore after next semester. So this is
This,
information. Yes, 6242 is being offered in the spring, but that is it. So I will send out an email as to what the plan is, because I'm not sure if this information has trickled all the way through the system, because these things have just been decided within the last few weeks. So watch out for that email so that I can educate you guys as to what the choices are, and hopefully you can forward that out to people that you know that would be interested. In the spring, I'm teaching this class again for the last time, and I'm also teaching longitudinal multi-level models. It's offered at 2 o'clock synchronously through Zoom on Tuesdays and Thursdays, and you are all welcome to enroll if you would like to come.
what are you teaching? Are you teaching anything this summer?
In the summer, I don't teach.
Okay. And then in the fall, which do you know what you're teaching this fall? Next
I,
fall.
I believe that I am going to teach the factor analysis and structural equation modeling course again, which you would all be welcome to come to. And I believe I am teaching the clustered version of multi-level models, which you are all welcome to come to. I would say if you're interested in taking the clustered multi-level, it would be helpful to have the longitudinal version in front of that. It's a lot of the same ideas, but the context in which the models show up is just different enough to where having both would be helpful. And more generally, if any of you have questions about what further coursework would be useful for you, given the types of data that you plan to work with, I'm happy to chat with you about that. So just shoot me an email or ask me questions whenever. So just as a, I'm not sure how I got on that topic. Oh, I know how. Fixed slopes to random slopes to next semester to this course not being a thing anymore. That's how I got there. Okay, I've reconstructed the pathway. All right. Anything else on homework or logistics or courses or anything? All right, then if not, we got some new stuff to talk about today. Are you ready for some new stuff? Why not, right? It's a bit of a rhetorical question, but you did come. You made the effort to show up, so I want to reward that effort by giving you some new stuff. So let me pull up lecture 5. Here we go. So we're transitioning into what is known more generally as multiple linear regression. So we'll have a bit of review for the first couple slides, and then the idea is starting to build models that have more than one type of predictor simultaneously so that you can pit them against each other to see what happens. Like if I have a predictor X that predicts an outcome, is X still important after I control for Z? Those kinds of questions about the net effect of predictors that are related to each other are able to be answered with these models. So we're staying in the family of general linear models, extending to more than one predictor at the same time. The good news is that there's very little in the way of new concepts here. So homework 5, I will tell you, is going to be easier than homework 4. Homework 5 is your chance to sort of go back over the things that you've learned and make sure that everything is feeling nice and solid. Homework 6 will be fun again. That's the plan. So all of your homeworks, by the way, are up. I have gotten all of them up. So if you want to take a preview as to what I'm asking of you, you can do so whenever you'd like. So away we go. As usual, please feel free to interrupt me if you have questions. I'm trying to keep the chat window open here, but in case I miss it, flag me down. I do want to keep this as interactive as possible, even though it's a traditional lecture. I don't know of another way to present this material, to be honest. This type of content doesn't lend itself well to group discussion or activities or things like that. Like this stuff is hard, right? And it wouldn't be fair of me to expect you guys to teach each other or any of those sorts of things that you might be able to do in content areas that are different than this. So please ask me questions. That's the only way that I can see if this process is working. Oh, wait. So a little bit of review before we jump into the new material. So the role of each predictor variable is to create a custom predicted outcome for each person. So based on your X, you get a custom value for what the model thinks your Y should be. And each predictor may require one or more slopes to be able to fully describe how it relates to the outcome Y. So just to review terminology, X are your predictors, Y is your outcome to be predicted. So situations in which a predictor's effect could be described by only one fixed slope would be if it is a quantitative variable and the effect is linear. So that's where we started, just looking at, say, what is a 1 unit change in X? How does that correspond to a change in Y? The slope coefficient gives you the expected change in Y for a 1 unit change in X. That's a linear effect. A single slope would also work if your predictor is binary. So if all you have to describe is the difference in the mean of the 0 group and the mean of the group coded 1, that's one fixed slope that directly captures that mean difference. So even though we talk about it as mean and mean difference, it's still a slope because it's a 1 unit change in X. For a binary predictor, a 1 unit change in X means you went from the 0 group to the 1 group. So if you have a binary predictor with a positive slope, that means the 1 group is higher than the 0 group. A binary predictor with a negative slope means the 1 group is lower than the 0 group. If you have more than one slope in the model, that may be because you have more than 2 groups. So for instance, if you have, we had working class self-rated group as one of the predictors in our last example where we had low, middle, or upper. If I have 3 means, that means my model has to have 3 fixed effects. One of those is the intercept. That's going to capture the mean for the reference group. And then I need 2 slopes to differentiate each other group from the reference group. That gives me all 3. If I had 4 groups, that means I need 3 slopes, and that's what's in your homework. If I had 5 groups, how many slopes do I need? 4, yeah, because the 5th term is always the intercept.
Okay, so the one is the intercept, and then the others are the, what is the word for it? The slopes. I know there's slopes, but is there some kind of slopes like they're the predictor slopes?
The fixed slopes of the predictor variables
okay.
that distinguish one group from another.
Okay.
So you would code up the predictor, like if you have group 1, 2, 3, 4, you would create new predictors that would be group 1 versus 2, group 1 versus 3, group 1 versus 4.
Mm-hmm.
And then the slopes of those predictors then give you those group differences.
Okay. Just trying to get the lingo.
The lingo is very important. Thank you for asking. Statistics is not difficult because of math. It's difficult because of working memory and trying to keep track of all of these words and how they map onto what we're doing. So are slopes equal to pairwise, or is that a given, or is that unrelated? It depends on your coding scheme. In the coding scheme that I've shown you, dummy coding as it's known, or reference coding, a slope is a difference directly between 2 of the groups. In other coding schemes, that may not be true. In general, it's however you set it up, you control what you then get back. Okay. And the formula for how many pairwise mean differences. By the way, one thing that I realized I probably should have put somewhere on a slide, but I didn't, is the idea of family-wise error rate or type 1 error control. Have you heard these phrases before elsewhere? Okay, not most people. All right. So this is one of the areas of statistics in which it's funny how people act inconsistently. So type 1 error, you guys know what that is, right? What's type 1 error? If I make a type 1 error, what have I done incorrectly?
Isn't that a false negative? False positive.
False positive.
False positive.
Yes, I have rejected the null hypothesis when I should have retained it, or in English, I have said there is an effect when there's really not one. False alarm, false positive, however you want to think about it. False negative is a type 2 error. There was something there, but I missed it. Type 2 error is much more likely in the social sciences because we rarely have enough power to actually find the effects that we would be looking for. Type 1 error is the thing that we control directly by setting alpha. So if we decide to have an alpha, which is a cutoff point of 0.05, what that means is that any p-value that is less than 0.05 we label as significant and therefore something we're allowed to talk about. Specifically in this context of group mean differences, someone will yell at you about type 1 error rate. I can almost guarantee it if you report all possible mean differences. Even though they are already given to you by the model in some cases or implied by the model as linear combinations, that will set off someone's alarm bells that you're testing too many things. If I have 20 different mean differences that I report, how many of them would you expect to be significant just by chance? This is another finger question. Just one. Type 1 error rate of 0.05 means 1 out of 20. In this context of group mean differences, people will worry about you reporting multiple p-values because you may end up with type 1 errors. Only here, though. You can have a regression model that has 20 different predictors in it, and that is fine. No one will say a word about type 1 error. So there are all kinds of old school techniques that people use to correct p-values or the standard errors that get them to you to make them more conservative. There's Bonferroni and Chaffee and Tukey and like all the old white guys that name the stuff after themselves. Like there's a million and one of these. I'm not going to waste my time with that because the second you leave general linear models, that stops being a thing. Those are techniques that are used in one specific instance and they're used inconsistently across general linear models. So what I will tell you is this. If you have a whole bunch of groups to be compared, let's say that you have a study that has 6 groups in it. Possible, not likely, but possible. That gives you, I believe, 15 pairwise differences. If you want to report 15 p-values, maybe pick alpha of 0.01 instead of 0.05. Just be a little bit more conservative if you know that you're going to be reporting a bunch of different tests because you don't want one of them out of 20 to be significant by chance. 1 out of 100 is a much more stringent cutoff. So I'm not going to worry too much about type 1 error inflation in the sense that I have to worry about it sometimes according to people, but not others. I think you have to worry about it all of the time. All of the things that we've done up to this point have relied on very few p-values because we've been focusing on one predictor at a time or one set of predictors at a time. Once you have a lot more stuff in your model or multiple outcomes that you're doing all these tests for, this is something that you may want to take into account in choosing your alpha level. So a bit of a caveat there, but I felt compelled to mention it. So any thoughts or questions about that? Basically, if you're going to report a whole shit ton of p-values, be more conservative. And you can pick some old white guy's method to do that with, or you can just set your alpha at a lower level, like whatever, I don't care. So for each slope in the story here, we get an unstandardized solution where we have the estimate minus the null hypothesis, which is typically 0, divided by the standard error gives us our t-value, and we get a p-value that goes directly with that. So each slope has a significance test that shows up automatically for it on your output. And we can also ask for some sort of standardized measure of effect size. So this is important to report not only whether a slope is significant, but some measure of effect size by which we can say in a more absolute sense how strong the relationship is between the predictor and the outcome. Because as you get more people, it gets easier and easier to find things to be significant. So if you're going to say this is significant and we're talking about further quantifying that with how large the effect is important. regardless of sample size, but especially when you have large sample sizes and you have a lot of power. So in the models that we've been looking at, one predictor at a time, say for a linear model, if x1, by the way, is a quantitative variable in this equation on page 3 of lecture 5, this would be simple linear regression, meaning just one predictor. And the terms that we've learned in the equation, beta 0 is our fixed intercept. It's the expected outcome when x1 is 0 specifically, because that's the predictor that's in our model. There are some semi-trick questions on homework 4 about this. The intercept is conditional only on the predictors that are currently in that model. So for instance, if you're past section 1 and you don't have control group and training group anymore in your model, nothing is conditional on control group anymore. SAS has no memory of what used to be in the model. So the intercept is only conditional on what is currently in the model. The beta 1 slope for the effect of x1 here would give you the change in y for a 1-unit change in x1 specifically. And we could ask for a standardized slope to describe its effect size. And in this case, the standardized version of beta 1 would be the same thing as the Pearson correlation. So there would be no real reason to estimate a model like this because the Pearson correlation would give you the exact same information. If I had a different model with a different predictor but the same y, then the intercept takes on a different conditional definition. More generally, the intercept is always the expected outcome when the predictors are 0, but what are the predictors? In this case, it's conditional on x2 being 0 because that's what's in the model. And the slope for x2 gives us the change in y for a 1-unit change in x2 specifically. And the beta 2 would be its Pearson correlation. So what happens if we start to put them together? That's going to be where we're headed today. In terms of significance testing, this is the new thing that we started talking about last week. The idea that we might want to have a separate general test of the model. So if we have more than one slope in the model, then we have f and r squared to pay attention to, right? Remember our friend f? F tells us how good of a deal we got with our shopping. F tells us a ratio of information captured by the model per slope it took to capture it over information not captured by the model per slope we could have used. And so that information idea, that's the numerator of the variance equation, what's known as sums of squares, model on the top, leftover residual on the bottom. You can also express f as a function of r squared with this, but basically it boils down to how good did your model do at predicting variability in your outcome. So this idea that we're weighting per predictor, this is going to show up to complicate our interpretation of the model if we have some predictors that aren't very good. Like if I have 2 predictors and one is useful and one is not, the F test for the model is going to be dragged down by the one that's not useful because it's information per slope. So if you have a good slope and a crappy slope, that's going to make your model look less good. So the objective generally is to include only slopes that contribute in the model and not necessarily include those that don't. And the effect size that goes with this is our friend R squared. So R squared tells us what proportion of the original outcome variability was captured by the model's predictors, was explained by the model, was accounted for by the model. Pick your synonym. You can also think of it as the square between the outcome that's predicted by the model, the y hat, and the one that's the actual outcome that has all the error in it. So we have a general test given to us via f and r squared. We have specific tests for each individual slope given to us by t, and we can convert that into an r or a d to give us a specific effect size. And as we talked about in your quiz last week, the model is the slope if you only have one slope. So f and r squared are redundant with t and the Pearson r for that much. Okay. With me so far? any of that you want to hear again or talk about? Okay, we have a new vocabulary word. This is a word that you already know as a layperson definition, but it has a specific meaning, and the word is unique. Unique is the new word for today. The idea is what happens once we put more than one predictor into the model at the same time. So not just multiple slopes for the same predictor, but multiple conceptually different predictors. So do you know what I mean by that distinction? So for instance, we had a piecewise model of education, right? We had one slope for the subset of people from 2 to 11 years, then we had a slope for 11 to 12, and a third slope for 12 to 20. So education as one idea took 3 slopes to describe it. Just like golf group as one idea takes 3 slopes to describe it. We're transitioning to like, what if we put golf group and enthusiasm in the model at the same time? So 2 or more conceptually different predictors, each of which may take 1 or more slopes. And so I've got examples of both of those cases, 1 or more slopes or not 1 or more slopes. So the short answer of what's going to happen is that we change the way that we talk about what the slopes mean. So up to this point, we've just said this is the fixed slope. This is the effect for everybody. Homework question. So if I have the slope from, year 2 to 11, that's the slope for everybody from 2 to 11. There's no distinction. It describes how education relates to income in our last example bivariately. So the word bivariate means just 2 variables at a time. So if I only have education predicting income, that describes a bivariate relationship. If I only have golf group predicting golf score, that's a bivariate relationship. Once we pit more than one predictor against each other, the relationships adopt the term unique. And unique means after controlling for the other predictors in the model. The idea of a net effect. And what's going to happen on the effect size version of this is that the standardized slopes that you get are no longer going to be the same thing as a Pearson correlation. Pearson correlation is a bivariate measure of association. Instead, they are going to be related to something that's known as a semipartial correlation. A synonym for semipartial is part, by the way, but there is yet a third kind that is called partial that is not the same. So more fun with terribly named constructs. I couldn't make this up if I tried. I couldn't make this up. But I've got a story for you, as promised. So this is my attempt to try and talk about the idea of common versus unique effects in the context of the real world, or at least the world that I wish I could live in every Tuesday night. This is the cast of This Is Us. So I asked last time, only a few of you are familiar with the show or like the show. Is that true? A few of you like the show? Who likes the show? Can I get a show of hands? Okay, a few people like the show. You don't have to like the show to understand the example. That's not required. But let me give you the background of the show here. The premise is that it's following the same family through time. So the same family is shown. The show opens when there's 3 adult children here. So there's Randall, there is Kate, and there is Kevin. They turn 36 years old. But then later in the episode, we see what looks like this whole other family when they were children, and lo and behold, it's the same family. So here is a clip on the bottom from when the kids are like 11 or 12, and we find out sort of by going back and forth what's happened to these people's lives. It's a really good show. And I just read the other day that Mandy Moore, by the way, for those of you who grew up in the 90s, you might remember Mandy Moore as one of the teen queens. It was Britney, Christina Aguilera, Jessica Simpson, and Mandy Moore was like the 4th on the totem pole. She had a couple of hits. Turns out she's a really good actress, and it takes her like 5 hours to get into makeup to be their mom. So she also plays them when they're adults. She's younger than they are in real life and is playing like their mom in the 60s. So it's a whole thing. I'm just saying it's worth the investment into the show. But let's say, just hypothetically, that with 3 teenagers, the house is a mess and Rebecca Pearson has had it. She wants them to be accountable. She wants them to clean the mess up. She's decided that she's going to offer an incentive system. So they would have been teenagers in roughly the early 90s. So I'm putting myself back into that form. And the incentive system is going to be based on Nintendo games. The original Nintendo game with the cartridges in the gray box, like that's what we're talking about here. So she comes up with an incentive system to get the kids to clean the house. And she says that for every room that each of you is responsible for cleaning, you get a new Nintendo game. That's a good prize. And if the whole family cleans at least 8 rooms of this house, so let's say that there's 9 possible rooms, there's 4 bedrooms, 2 bathrooms, 1 living room, 1 kitchen, 1 dining area. If there's at least 8 rooms out of 9 cleaned, the family gets a new TV. So there's an incentive to work together. There's an incentive for each person to do as much as they can. And let's say she goes out shopping to do her perfect Rebecca things, and she comes home and the house looks nice, and so she tries to find out what happened. So here's my prediction as to what would have happened based on the characters of the show. See, those of you who like the show will understand this prediction. Well, it turns out that all 9 rooms are clean, so the family gets a new TV. Hooray. Now, what do they each get in return for their individual efforts? That's the question. So if we start with Jack, the dad, and Kevin and Kate, each of them said that they cleaned their own bedroom, and no one else claimed that they cleaned those rooms. So they each get 1 Nintendo game. Now, Jack also said that he cleaned the kitchen and the dining area, but Randall said he did that too. And Kevin thought he cleaned the living room, but Randall did that too. And Kate thought that she cleaned the living room, but Randall did that too. So we can't give any of the kids or the dad Nintendo games for the rooms in common. And Randall, of course, being the overachiever that Randall is, he would have cleaned the whole house had he had enough time. But he cleaned 3 unique rooms that no one else said they cleaned, so he gets 3 games. So the idea of this is who gets credit for what? When there's overlap, you can't give credit to any individual reliably. But the fact that all of the rooms got clean still matters. So we want to find a way to think about sort of the individual contributions of each of these people who are going to be the predictors, as well as the joint effect, factoring in the redundancy. How well did the predictors do? That's going to be my story for variance accounted for. So we're focusing on 2 things. General utility of our models. So how many rooms in the house got clean? That's another way of saying that is how big is our R square, right? Instead of variance accounted for, it would be like dirt accounted for. Dirt accounted for and removed, more specifically, not just swept into a closet or under the bed or what have you. So how many rooms got clean on the whole? What proportion of the house got clean? That's your R square. And individual effort goes into that and joint effort goes into that. So even if we don't know for sure who cleaned which room, so long as we know that it got cleaned, that counts towards the total. So the R square for models that have multiple predictor variables the R square is going to take into account both the individual predictor contributions and their joint contributions that no predictor is going to get credit for. But we also do want to know about the individual contributions. Most of the time, hypotheses are phrased in a way that says, after controlling for something that we already know should matter, what is the contribution of this new predictor that is the focus of my research? A lot of questions are phrased from that perspective. And that's a question about individual contribution. Did this kid clean a room that no one else did? Does this predictor add to the prediction over and above the information that's already there? So for instance, we know that babies who are born to moms who smoke have worse outcomes in a variety of health and cognitive domains. But is it the smoking? Right? Because we can't take pregnant people and randomly assign them to smoke or not. The IRB is not going to be down with that. So is it the smoking? Is it the nicotine and the carcinogens and all the stuff that affects the baby in utero? Or is it all of the things that coincide with a mother's decision to keep smoking or start smoking while she's pregnant, which is correlated with socioeconomic status, lack of education, et cetera, right? So in trying to pull apart how much of it is the smoke and how much of it that smoke is just a proxy for other things that are related. So we might want to control for the mother's education level, some measure of their income or access to health care or things like that, and then say, okay, now is there still a difference between babies who had smoke in utero versus babies who didn't? Can you think of examples from your own research that are phrased this way? Does something still matter after controlling for something else? Yes, you're nodding. Kaylin, do you want to play?
I was trying to find unmute. So one of the things I do with with research right now is looking at how like adverse stress experiences affect identity development in trans individuals. And I previously looked at it in just like genderqueer individuals in general, but we have to like control for other adverse experiences that they might experience that aren't related to like adverse childhood experiences. And we also have to control for like age and like income and stuff like that, and whether or not those have effects. So, and then like try to see what's left over.
Yeah, that's a great example because there are things that may be sort of general factors, so to speak, and then there are unique factors based on particular individuals' experiences. And so to be able to say that no, it really is the unique things, the individual experiences, we have to control for the stuff that should affect everybody. Age is a classic one. I used to work in cognitive aging, and chronological age was the first thing in the model, or someone was going to yell at you because it is uninteresting to say things like older people are weaker, older people are sicker, older people tend to do less well on these tests, right? That is not interesting. What was interesting was if you could put in other predictors that made the effect of age go away. That's where it gets interesting because then it's like, no, it's not being older, it's being in worse health. It's being someone who hasn't had access to adequate medical care throughout their lifetime. It's what is age related to? Gender is a great example of this, right? There's very few things in life that like your XX or XY chromosome or whatever combination you happen to have is going to actually matter. It's all the stuff that goes along with how people are socialized and treated differently because of their gender identity that relates to things. I've heard of people say the same thing about gender, that they'll be happy when gender is no longer a significant predictor because they would have actually figured out what it is, what gender is related to that matters. So these sorts of, no, really, what is it kinds of things, that's what these models are designed to get at, is what is the specific utility, what is the unique effect of the predictor after controlling for other things that are related to it. Having experienced political events and laughing. Yes, exactly. So other examples that you can think of or that you want to share? But you get the idea, right? If you read research papers, a lot of hypotheses are phrased this way. Does this thing matter after factoring in this other stuff? And anytime that you want to be able to say something like that, all of it has to be looked at simultaneously in one model. So a way to describe common versus unique contributions is these sorts of Venn diagrams. This is what's known as a Ballantine image. And this describes visually how two different predictors relate to an outcome. So in this case, I've got an x1 and an x2, and they're going to be pitted against each other in a model predicting y. So the whole part that is captured by these variables that is not e. So e is left over, right? E is your residual. E is the difference between what the model says your outcome is and what it actually is. E is error, noise, unexplained, unaccounted for, all that stuff. So anything that's not E was accounted for by x1 and x2. So the proportion of variance that they get together would be my R square. But in looking at how useful each one is, B describes the area of x2 being related to y that has nothing to do with x1. So B is how much of the prediction is due to a unique effect of x2. Likewise, A describes the same idea for x1. And this C part is the I can't give anybody credit for it. They overlap. C is related to Y, but I can't say who should get credit for that part of variance. So this sort of, the term for C is shared variance, covariance, collinearity, by the way, that's a word you're going to see. Collinearity is sort of a bullshit term. We'll talk about that in a few slides. Yes, I have an opinion on that too. Aren't you surprised? Collinearity is a problem that's not a problem anymore. How two different predictors, what a diagram? Is that a question?
Yes, I'm sorry, I just didn't catch what you said.
The diagram is trying to explain how x1 and x2 as two different predictors relate to y. So the circle that has all the letters in it is meant to capture all of the variability in y, and that variability has been partitioned as due to four sources. A is x1 only, B is x2 only, C is either one. So like both Randall and Jack thought they cleaned the living room. We don't really know who did it. We just know that the living room's clean. And E is the part of Y that has nothing to do with x1 or x2. So E is the idea of a residual, the leftover information, the deviation from the regression line that each point still has. So R square is going to take into account this C overlapped part, but the test of significance for each slope is not.
Okay, just to make sure I understand. So then E is the three or like the four different bedrooms that they had. In A, C, and B, it's like the living room and the kitchen.
Y is the house.
Okay.
So Y is the house, yes. A would be, and B would be like each kid cleaning their own room. C is the living room that everybody thought that they cleaned. So it got cleaned, we just don't know who cleaned it. And in my previous example, all the rooms got cleaned, and so there would be no E part. But if there were any rooms that were still dirty that no one did, that would be E. Okay, how are we doing so far? Okay, so unique effects, that's the new terminology. Like how x1 relates to y by itself is a bivariate effect, just the two of them. Just the two of us. We can make it if we try, just the two of us. See? Welcome back. I promised you I would sometimes sing. But yes, x1 and y, just the two of them, bivariate. x2 and y, bivariate. And we put it all together, and then we're talking about how x1 relates to y uniquely after controlling for x2. Uniquely. And here's some math. So this is what I said with math. So contrasting how these terms get found in a one predictor model versus a two predictor model. So if I just have x1 predicting y all by itself, then here's how you would find the fixed intercept. The role of the intercept is just to adjust for mean differences between the variables. It gives you what the expected outcome should be when x is 0. We can get the slope directly from the Pearson correlation, and we can convert back to a standardized slope, which is the same thing as the bivariate Pearson correlation. The math gets a little bit uglier when we have a two predictor model, but the concepts are still the same. So beta 0 is going to give us the expected outcome when both predictors are 0, so taking into account both means, and the standardized slopes for each of the predictors is the relationship between it and the outcome minus the part that's in common. So the part that's in parentheses here is like the C part, the part that it can't get credit for. And that works the same way for both of these things. So the standardized slopes, when you have both predictors in the model at the same time, are not going to be the Pearson correlations. They get a new name. And their name, you can either have a standardized slope as a measure of effect size, or you can have a semi-partial correlation. They are related to each other, but they're not exactly the same. In these models, there are multiple ways to give effect sizes, and I'm going to try to give you a menu to choose from because some of them are easier to get out of software than others. So standardized slopes or semi-partial correlations can provide effect sizes in these cases. So what is a semi-partial correlation? It's the idea of unique correlation. So for instance, area A would correspond to a semi-partial R square. So semi-partial correlation squared. The latter is how much of the R square is due to that variable by itself. So I like this one the best. It's not as common outside of these models because there isn't always just one kind of variability, but I think conceptually this is one of the easiest ones to keep track of. If I have, say, an R square of 10%, let's say, actually, let's do it in scaling with the diagram. Would you say that this is maybe 60-40? Can I do some PowerPoint estimation here? I'd say that A, B, and C are like 60% and E is 40%. So based on me just staring at this picture and making up some numbers in my head, it'd be like of the 60%, so of the total of the variability in Y that is related to X1 and X2, I'd say A would maybe be like, let's say a third of it. So like of the 60%, it's not of, let me say it this way, it's not a proportion. 0.2 of the variance is due to A, 0.2 of the variance is due to B, and the remainder is due to the overlap. So it's an amount. So what is the R-square contribution of that predictor specifically? That quantity is known as semi-partial R squared. And we will find ways to make the programs get all of these numbers for us. Do not worry. One side note, semi-partial, a synonym for this is a part correlation. But partial correlation is another thing. Partial does not really help us here. What it does is give you the correlation of the predictor and the outcome controlling both for all the other predictors, not just controlling the predictor. That quantity doesn't really correspond to anything of interest in terms of the model, and so I'm not going to spend any time on those. But this is one of those things where you have to be careful in your output because you will get tables for both. You will get a table that says semi-partial and you'll get a table that says partial, and so you'll want to make sure that you look at the semi-partial one. In particular, with stata, this gets tricky because stata procedures give you partial directly, but you have to do some actual calculation to get semi-partial in a few instances, unfortunately, but I will show you how to do that. So semi-partial correlation squared is how much of the R square is due to that variable prediction uniquely as your new effect size. Here is how all of these things get calculated. So in case you're wanting to see the math behind the ideas, standardized slopes are related to semi-partial correlations in that they share the same numerator, but the denominator is different. So they won't give you the exact same number, but either one will give you an effect size that you can interpret relative to the other predictors in the model to say which one matters the most. So you would stay within a family. If you're going to use standardized slopes, you could compare across those. If you're going to use semi-partial correlations or their squared versions, you can compare across those. I wouldn't mix and match though, because that would be confusing. Here's how R-square gets computed in these models. I've given you a couple different versions of the formula that I found because some of them I think are more intuitive. But the bottom line here is at the bottom of the slide 14. Your R-square for the model is going to be a combination of how well each individual predictor did plus what they had in common that none of them get credit for. So common does go into R-square. You just can't see any individual slope get credit for it. So the kitchen got clean. We don't know who did it, but the kitchen is still clean. We just can't hand out Nintendo games to any one person because it's ambiguous as to who cleaned the kitchen, but we all know it's Randall. I mean, come on. There's no other alternative. All right. Enough math for now. So in terms of knowing what to do with the numbers that come out. So if I have a model that looks like this, if I have x1 as one of my variables, beta 1 is going to give me the linear effect of x1, and beta 2 is going to give me the linear effect of x2. Beta 0 is my intercept, my you are here sign, and it is now conditional on both of my predictors being 0. So same rule as before, just with additional conditions. When every predictor is 0, that's what beta 0 indicates. The way that we talk about the effect of x1, it's not just the expected change in y for a 1 unit change in x. It's the expected change in y for a 1 unit change in x after controlling for x2. You have to tack on that unique idea. You wouldn't necessarily have to say that in each sentence, but at some point you would have to say, the unique effect of each predictor can be described as follows. And the idea is that it's after controlling for the other, any common area, any overlap. So what this means is that the Pearson bivariate correlation between x1 and y is going to be different than the standardized slope or the semi-partial correlation whenever x2 and x1 are related. So the only situation in which you would get the same answer for what beta 1 is, regardless of whether x2 is in the model, is if x1 and x2 have nothing to do with each other. Do you follow what I'm saying? Not yet, maybe. Let me go back. Go back to the earlier thing. So if what I'm talking about is a model that only has one slope, so I might go back to slide 13 for a second here. So beta 1 in the first equation versus beta 1 in the second. That's what I'm talking about. The only situation in which that beta 1 would take on the same result is if x1 and x2 are unrelated. If there's no overlap, then it doesn't matter if we've controlled for x2. The way that x1 relates to y is the same. It's only when x1 and x2 are related to some extent that the effect that a variable has is going to depend on what else is in the model. And this is going to be a function of the design of your research project. So let's say that you have an experimental design where you have, say, a treatment group and a control group, but you're also assigning people to some other dimension. Let's say that you're sampling younger adults and older adults. If you randomly assign older and younger adults to treatment and control, and you have balanced sample sizes, then older versus younger is going to be uncorrelated with treatment versus control. And so then the effect of each is going to be orthogonal. They're not going to depend on each other. In almost every other instance of observational data, your predictors are going to be related to each other. and therefore their effects are going to be different as a function of what else is in the model. Okay, does that help? Maybe? Okay. We'll see what happens in an example. So these slopes are scale dependent, the same as usual. So it depends on what a unit of x is and what a unit of y is to interpret what the results for the slope estimates are going to be. That's why we need standardized slopes or semi-partial correlations to be able to describe how they relate in a more absolute sense to the outcome. Standard errors. So standard errors, we all know what a standard error is, right? Or we're going to know by the end of the semester, one of the two. Standard error tells you how far off on average the sample whatever is from the population whatever. And do you remember how we say whatever in stats language? Parameter, yes, very good. So previously, we looked at how standard errors are computed in these models. They're meant to describe how variable across samples of the same kind your slope would be. So if I redid this study over and over again with the same sample size and the same kind of people, how wiggly would my beta 1 estimate be across samples? That's what the standard error is meant to convey. It's the standard deviation of the sampling distribution for that slope across repeated samples. And the things that went into it, residual variance of y. So all things being equal, if there's less variance left over, there's a smaller standard error. So less variance, less error, that seems reasonable. Sample size goes into the bottom. So big N here, more people, smaller standard error. And the variance of the predictor, because the standard error is in units of y per units of x. And so this basically takes the units off when we build our t. So we have a slope that's the change in y per unit change in x. We take that slope and divide by the standard error that's in units of y for units of x. When you divide by a fraction, you flip it upside down. Here's the reciprocal. Is that the right word, math people? You flip it the other way, and the units cancel. So then you end up with your t-test statistic that is unitless. The same thing is going to happen in a standard error for a model that has more than one predictor, but there's an additional term that shows up here. And it corresponds to how much variability is in the predictor that is not in the other predictors. So like if you built a new model where you had one predictor as the outcome and all the other model predictors in it, the R-square for the model is what this term is getting at. So how much variability exists in the predictor unique to it. And the smaller its unique variability, the larger its standard error. So this is the basis of problems of collinearity. Basically, in English, the more something has in common with all the other predictors in the model, the harder it is to figure out what its unique contribution is. Overlap makes things messy. And so if there's a lot of overlap, if your predictors are highly correlated, the standard errors for their unique effects are going to be higher because it's harder to figure out what their unique effects are if they're really related to each other. That's not a problem, it just is what it is. So the best case scenario is that you put in predictors that are unrelated to each other, and then it's as easy as possible to figure out what each predictor's unique effect is. That's the basis of having equally balanced cells in experimental conditions, by the way. You're creating predictors that are unrelated to each other when you do it that way. All right, so these are going to be my effect sizes, standardized slopes, or squared semi-partial correlations. Those are the ways that you can easily get your software to give you effect sizes for each individual slope. We will still have an f-test and an r-square for the overall model. And by the way, there is something else that will show up on your output called omega squared. That is the analog to the sample size adjusted correlation or r-square version. So if you're reporting those as your summary statistics, you'd want to report omega squared instead of just the regular semi-squared, squared semi-partial R. So we can get these in SAS a couple different ways. We can use procreg. We can also get them in contrast statements, and in Stata, there's an option called pcore that we're going to use to get squared semi-partial correlations. Here is a catch though. Even though your output is going to give you standardized slopes or squared semi-partial correlation effect sizes for all the slopes, they're not always the right way to think about it. In particular, the slopes that work together to describe the full effect of a predictor, their semi-partial correlations should be lumped together because they're related to each other. So for instance, if I have a model that looks like this, if I have age and age squared, so that would create some sort of curvilinear effect of age. To be able to talk about what is the net effect of age, age isn't just beta 1 or beta 2. Age is both. So I gotta ask for the lump, the joint test. So I will show you as the one new piece of code, I think, in this unit, how to ask for an F-test that lumps those two predictors' effects together and gives you an effect size for their joint contribution. So this is necessary whenever you are asking for a test of more than one slope, but fewer than is all possible in the model. So this is the one new thing I'm asking you to do in terms of code for homework 5. The same thing is true in a model like this, where beta 1 and beta 2 work together to describe the impact of our 3-category grouping variable. So we got to lump them together in talking about their significance and their effect size. So the lumping, I will show you how to do. All right. How are we doing?
Can I ask a question about the lumping?
Yes, lump away.
So is it the type of thing that I'm assuming Stata and SAS will let you lump whatever you want to together? And so you need to be intentional about what you're doing and why you're doing it.
Yes, exactly that. So in SAS, lumping is going to be accomplished with a contrast statement, and that will directly give you an F-test for the significance of the lump, as well as an effect size in terms of semi-partial correlation squared. How much of the R square is due to the lump? The joint hypothesis test, by the way, would be the lump. A multivariate wald test, as it's called. In Stata, though, there is an analogous test statement that will give you the F-test of the lump, but it doesn't give you the semi-partial correlations. You have to actually run a reduced model without the lump in it and compute those yourself.
Got it. Thank you.
And because it's inconsistent across programs, I am not asking for semi-partial correlations in any of your homework. But I am going to ask for F-tests because those are easily done in either program with the piece of code. So I will show you how to do all of those things. So this idea that we are putting in more than one predictor and letting them duke it out for who gets the unique credits for things, this is what's known as multiple linear regression, more generally. These same concepts as trying to keep track of which terms need to be lumped together also show up in a version of the same set of models that's known as analysis of covariance. So you've heard of analysis of variance, right? That's when you have a grouping variable, that's what it's called, as your predictor. Analysis of covariance is when you add another quantitative predictor also at the same time. ANCOVA, exactly. So for instance, if I had a model that looked like this, I have my beta 2 and beta 3 distinguishing the lower group from the middle group and lower from upper, and I want to throw in a covariate. So analysis of covariance uses the term covariate to mean a quantitative variable that someone else cares about who's not you. Control variable. Whether or not you want to care is up to you, by the way. Like, you can have a covariate you care about, but then you'd call it a predictor. You wouldn't call it a covariate if you cared. So this would be like, I have to control for age, or I have to control for parents' education, or I have to control for something that someone's going to yell at me about. So beta 1, 2, and 3 all together are my model, right? The three of them working together. How well do the three slopes work together to predict my outcome? How much variance do they get together? Like, the model is like the highest order lump that you can have. And you automatically, by default, you get an F test for that, and you get an R square for that. What I'm talking about is drilling in deeper, because in addition to knowing whether beta 1, beta 2, and beta 3 work together, I might also want to narrow in on just beta 2 and beta 3, because that gives me whether group matters. Beta 2 and beta 3 as a subset represent a substantive interpretation of whether or not there are differences across my three groups. Beta 2 and beta 3 give me all three possible differences. So to lump them together, that's the new pieces of code that I want to show you. It's contrast in SAS and test in Stata. It's more generally known as a multivariate walled test. And the F version in particular, there's also a chi-square version that doesn't use denominator degrees of freedom. So that's what we're going to do as our new thing. By the way, those of you who have had regression in previous coursework, what I'm actually talking about is an end run around what's known as hierarchical regression or stepwise regression. Because in those procedures, you start out like you would say, for instance, you'd put X1 in the model by itself, see what happens. Then you'd add in beta 2 and beta 3, and you would get an R squared change test for that contribution. What I'm showing you is a way to get all of the information from both models from one model. You don't have to enter it in stages. You can do the lumping out of that model. Because if your lump test of beta 2 and beta 3 is significant, that's the same thing as saying the change in R square that results from adding those two things simultaneously is significant. So this approach is going to generalize to more complex models for longitudinal data, multivariate data, clustered data with latent variables and things like that, whereas hierarchical regression does not generalize in the same way. So this is a more general approach than what is typically presented. So you get to see that. Unfortunately, in Stata, the effect size that goes with the lump is something that you're going to have to compute yourself. Again, I'm not asking you for that on homework, but I wanted you to be able to do it. So I have these steps illustrated in the examples that we're going to follow. So that's what we'll do. All right. So, big picture. What are we doing in this unit that I think will last until Thanksgiving? Not a rhetorical question. What's the big picture of what we're talking about now? What are we doing that's new and exciting? Multiple predictors, yes. So we can have each predictor have only one slope, or each predictor could have more than one slope. The idea is to pit them against each other to find out what does each predictor contribute to the model uniquely. What did it do that no other predictor can do? And have a test of whether or not that's significant. That's what we're working on. So in terms of life strategy, the examples that we've done up to this point, I would also do in life. So in these sorts of analyses, in these models as well as in more complex models, the logic is the same. You want to be able to say, if a predictor does not relate to an outcome, is it because it's just not related? or it's not related anymore after controlling for something else. Those are two different things. So to be able to piece them apart, the first thing that I always do is look at the bivariate relationship between a predictor and an outcome. So does education predict income? Does maternal smoking status predict child outcomes? Like, just bivariately, are these things associated, and how are they associated? And then I would put together a model or two or three that answers questions about unique contributions. And then I can say, yes, age significantly predicts cognitive status. However, after I factored in access to healthcare, the effect of age was no longer significant, indicating that it doesn't matter anymore. So I would have to have a model that has just age as a predictor and a model that has age and the competing predictors to be able to say whether or not age doesn't matter or it doesn't matter anymore. So the things that we've done, sort of looking at one predictor at a time, is a reasonable strategy to go forward. So unique does not necessarily mean significant. Unique means individual predictor, but there are other tests of significance. Yes, the term unique is referring to the contribution of the predictor by itself that no other predictor in the model can do. How many rooms did X1 clean? How many rooms did Randall take care of? Now that contribution that's unique could be significant or not significant. Yes. So significant is still just a label as to whether or not we're allowed to talk about it. But what the slope conveys is what the conceptual interpretation of the slope beyond just change in y for 1 unit change in x. Unique change in y. That's what we're doing. All right. Other thoughts or questions before we wrap things up?
I have a question, please.
Yeah, sure.
So before we add on the other predictors, do we run a bivariate test first for each separately, and then we're putting it together?
That's what I would do.
Okay.
And just because something isn't, like if you found out that a predictor doesn't matter bivariately, that doesn't mean you can't continue using it. There are situations in which it's not related bivariately and its relationship increases in the context of a full model. That is known as suppression. And that's one of the things we will talk about, that's unexpected results. So it's not that bivariate is like a threshold you have to cross, but it's just useful to know. Are these things related or not? And if so, how? Now, how are they uniquely related after controlling for this other stuff? Two different questions.
Okay. So don't drop it automatically just because it doesn't look useful in the. Okay.
Yeah, and there's situations in which it may not matter per se, but it could be a significant moderator of something else in the model. And that's the last topic that we'll have after Thanksgiving break.
Okay, thank you.
All right, other questions? All right, then I can see from your faces that we are out of time. We've hit that point in the energy cycle. So thank you for coming. Take care of yourselves and let me know if you need anything. See you Thursday.